This is really a remarkable chemistry lecture room that I'm used to have such very steep climb. But it makes it difficult for the professor because he has to head way up like rather than that. So you have to realize that. But it's been a delight to discover amazing university here that's a huge chemistry department, 18 categories of chemistry, and so much is going on in broad range and the depth of looking into different kinds of chemistry. Those things are very, very impressive. I'd like also to thank the superb Science Festival staff who have done excellent work in orchestrating this festival with special changes to Viola Igalikova. 4 days ago, we were in St. Petersburg, and here we had a chance to stop at the university where Mendeleev worked. Many of you may have seen the bronze statue of Mendeleev there. I wonder how many have seen him in St. Petersburg at that statue. How many? Not very many. But have you noticed then that it's his people who have looked at it rub the toe? And let's see, I'll show you. There's the, and you see that shiny, shiny toe? Well, if you look up higher, you would see that his nose is also shiny.
Do you have a pointer on that?
Well, I don't know if I have a pointer on it, but at any rate, maybe so.
Is there a laser pointer?
It may be a laser pointer. Whoops, all right. Turned it off, sorry. Excuse me. Oh, pointing it up there, good. Then we'll go to this.
Pick up the mic.
And then, yeah, all right. Go back one. And so someone must crawl up. People would have to climb up this pedestal to reach his nose, right? Now, at Harvard, John Harvard statue, which is looked at all the time by tourists and students and so on, they also rub the toe of John Harvard. That's to bring luck for exams and so on. And so that must be the reason, I presume, that you have rubbed the nose, his feet, but did you run his nose?
Of course.
Really? So you climb up and rub the nose? So that's traditional to do?
Of course, I've got two friends to help me to reach this point. That was...
Okay, so two friends helped him up to rub the nose. How many other who did that? Not many.
Have you had good luck because of it?
I can't say.
You hope so.
I hope.
Yeah. Well, another remarkable thing about this classroom, which is used for chemistry a lot, isn't it?
Yes.
Well, where's a periodic table hanging? Oh, way over here. Sorry, beg your pardon. Yes, good. Yeah, you do need a telescope at the top to look to read it well enough, but it's okay. That's fine. So let's see. Also, a few steps away from his statue here. Should be one more slide. Huh, it's not moving. Okay. Let's see why. Now, that's what we wanted to see. That 2 decades, it's told that since the statue of him was made, they added the periodic table up on the wall. So that was a good thing to do. Now, the week before we were in St. Petersburg, we visited San Sebastian in Spain, in the Basque country of Spain. We traveled to the nearby town of Bergara, where tungsten was discovered in 1783. That was one of the ones that, of course, Mendeleev had. True to the Basque food tradition, a team of bakers from the village created a delicious dessert to celebrate the discovery of tungsten. So here it is. Doesn't this look like tungsten? It looks just like it. It's a chocolate cupcake. And everybody in the town eats this.
Yes, with
So,
sugar crystals.
with sugar crystals sparkled on the top. And of course, you know what happens. One of the very valuable things about tungsten, we make tungsten filaments in light bulbs, right? And so all this time, they've been making light bulbs out of tungsten and a few cupcakes. Yeah. So yes, that reminds us that cupcake like that reminds that that reminds that the top of the sparkling cupcake has lighted the whole world and for decades and decades. Now I'll show the video of my talk celebrating Mendeleev. In addition to the periodic table, Mendeleev made many other contributions to science and the general things in the culture and politics. But one special contribution to science, I'll mention it in the video. So he was a very remarkable fellow, did so many different things, and we'll get, I should put this closer, I hope not. Just treat these 2 things, something about periodic table, and one area that many people may not recognize until now. So we can go on to Cecilia, to celebrating video.
The United Nations has proclaimed 2019 as the International Year of the Periodic Table of Chemical Elements, one of the most significant achievements in science. The periodic table was discovered 150 years ago by Dmitri Mendeleev. My talk today will have 2 parts. The first will be describing Mendeleev's pursuit to become a professor and his attempts to organize chemistry for the benefit of his students. I will briefly examine the periodic table, including the super heavy elements made by the Freyhoff lab of nuclear reactions in Dubna. The second part links to Mendeleev's consulting for Russian petroleum industry, which had a major role in his career. That industry was one of the most important sectors of the economy, as it still is now. From geological evidence, he concluded that oil was not created from fossil fuel, but emerges from the vast pressure cooker within the earth. Since then, most Russian geologists hold that view. It was also taken up by Thomas Gold, a cosmologist, who published in 1999 a book titled The Deep, Hot Biosphere. That led me to suggest an experiment to test an aspect of that theory. As part of the 2019 celebration of the periodic table, the journal Science dedicated its February issue to this subject. It includes articles ranging from hard-won discoveries and the hunt for new chemical elements. The cover of the issue displays a plaque located in Bratislava, Slovakia, honoring Mendeleev. In previous years, postage stamps of many countries have honored him. Here I show a couple. Before discussing this periodic table, I want to consider the incredible early life of Mendeleev. A fine biography by Mikhail Gordon is available. Dmitri was born in February 1834 in a small village near Tobolsk in Siberia. He was the youngest of 17 siblings. His father, Ivan, was a school teacher, but he became blind and died in 1847. His mother, Maria, then restarted her family's abandoned glass factory, but it was soon destroyed by fire. Mendeleev, at the young age of 13, had attended the gymnasium in Tobolsk. His mother was determined that her brilliant Dmitri would receive the education his promise deserved. In 1849, she took him, at age 15, across Russia from Siberia to Moscow. It was a laborious 2,000-kilometer journey, often on rides hitched on horse-drawn wagons. Alas, when they arrived in Moscow, the university did not accept Dmitri. Maria and Dmitri continued traveling another 650 kilometers to St. Petersburg to his father's alma mater. The Mendeleev family, poor now, relocated to St. Petersburg. In 1850, Dmitri entered the Central Pedagogical Institute, the main training college for high school teachers. He was given a small government scholarship. Soon after that, Maria died. He took her last advice as sacred. Quote, refrain from illusions. Insist on work and not on words. Patiently seek divine and scientific truth. Unquote. After graduation in 1855, Dmitri qualified as a teacher, taking the gold medal for the best student of his year. But he had contracted tuberculosis, causing him to move to the Crimean Peninsula on the northern coast of the Black Sea. While there, he became a science master of the Simferopol Gymnasium. In 1857, he returned to St. Petersburg with fully restored health. In 1859, Mendeleev secured a grant to study abroad for 2 years. Working in a laboratory in Heidelberg, Germany, he discovered that every gas has a critical temperature. If the gas is heated above that temperature, no amount of pressure can turn it into liquid. Also, he had the opportunity to take part in the first ever International Chemistry Congress held in September 1860 at Karlsruhe, Germany. The Congress settled a means to assign the relative weight of all elements, with the lightest known element, hydrogen, assigned as a weight of 1 unit. This crucial notion of relative atomic weight was essential for discovering patterns among the properties of the chemical elements. On his return to St. Petersburg, Dmitri took up a teaching post at the Technical Institute. He found that there was not a Russian textbook on modern organic chemistry. Desperate for money, he wrote a textbook, completing 500 pages in just a few months. He submitted it for a prize and won the prize. His students were also enthusiastic about its clarity. In 1865, he became Doctor of Science and achieved tenure in 1867 at St. Petersburg University. He took on the large lecture inorganic chemistry course, which he called General Chemistry. It led him to produce the definitive textbook of his time, titled Principles of Chemistry. It was destined to go through 8 editions. Moreover, the periodic table emerged from his organizing of his book. In February 1869, the 63 known elements each were identified by the relative atomic weights determined via the Karlsruhe Congress. His fledgling textbook was to be in 2 volumes. Volume 1, recently sent to the publisher, was mostly about chemical practice. He had treated only 8 elements: oxygen, carbon, nitrogen, and hydrogen, chlorine, bromine, iodine, and fluorine. His volume 2 began with the alkali metals, the sodium family, and alkaline earths, the calcium family, and noted the pattern of the halogens, the chlorine family. In thinking about the patterns among the elements, Mendeleev proposed a system of classification. What must have been considerable work, he sent a draft of a single sheet to the printers on 17 February 1869. This sheet was entitled An Attempt at a System of Elements Based on Their Atomic Weight and Chemical Affinity. It was printed in both Russian, 150 copies, and French, 50 copies, and sent off to many chemists. The information on this sheet was the essence of the periodic table. He put 3 question marks where he predicted elements that had not been discovered. Eventually, they were scandium, gallium, and germanium. Today, the periodic table is governed by the International Union of Pure and Applied Chemistry, IUPAC, they call it, IUPAC. Here I show a very large periodic table displayed at the University of California at Berkeley next to a standard IUPAC table. The numbers stand for the element's atomic number, Z, the quantity of protons in the nucleus of each atom. These positively charged particles, the protons, determine the number of orbiting electrons whose configuration is largely responsible for the chemical properties. There are no gaps in the Z number boxes for the IUPAC table up to Z equal 118. However, many heavy elements do not exist on Earth. The heaviest element found at any appreciable amount in nature is uranium, with Z equal 92. Beyond that, scientists must create new elements and accelerators, usually by smashing a beam of light atoms into a target of heavy atoms. If the nuclei of the light and heavy atoms collide and fuse, a new element is born. For example, element Z equal 101, named for Mendeleev, was made at Berkeley in 1955 by bombardment with helium ions of the element of Z equal 99, named for Einstein. The super heavy element factory in Dubda has added several synthetic elements to the periodic table, including Z equal 118, the highest one we have till now, and named for Yuri Oganessian. He and his team are now pursuing Z equal 119 and Z equal 120. Many varieties of periodic tables have been for fun. The Harvard Chemistry Department has posted one for vegetables. An American singer, songwriter, Tom Gare, has celebrated the periodic table with his song, The Elements.
Here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury and molybdenum and magnesium and dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium, berkelium, and also mendeleevium, einsteinium, nobelium, and argon, kryptonium, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered. Thank you. You may be interested to know that there is an older, much earlier version of that song, which is due to Aristotle, and which goes like this. There's earth and air and fire and water.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendeleevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
Coming to part 2, I celebrate Mendeleev's view of petroleum. He suggested that petroleum comes up from the depths and could be derived from metallo-organic reactions with water. He discounted oil emerging from fossils from rotting of plants and animals for millions of years. His view is compatible with aspects of the book by cosmologist Thomas Gold. Here I display some basic assumptions made by Gold and comments by Mendeleev. In recent years, much evidence supports this presence of a deep biosphere distributed on Earth in both terrestrial and marine settings. Gold's book and Mendeleev's views led me to suggest an experiment. It was carried out in 2004 at the Geophysical Lab at the Carnegie Institution in Washington, D.C. The study was specially designed to detect methane formation under geologically relevant conditions for the Earth's upper mantle. The starting materials were natural carbonate calcite, plus a bit of iron as catalyst and distilled water. These were loaded into a diamond anvil cell. High temperature conditions were produced by laser heating. High pressure in the cell was measured by use of a ruby fluorescence monitor. The temperature ranged from 500 degrees Celsius to 1500 degrees Celsius, and the pressure between 20 kilobars and 110 kilobars. Those pressures and temperatures correspond to depths below the Earth's surface, between 80 and 350 kilometers. Raman spectroscopy exhibited clearly the presence of bulk methane, shown by the CH stretching vibration of methane. The spectra also displayed a broad OH stretching of ice or liquid water. Moreover, very notable was the extensive bubble formation that accompanied decompression of the samples at room temperature. Further analysis indicated that the bubbles are predominantly methane. The bubbles of methane contributed at least a little to the Carnegie Institution launching in 2009 a deep carbon observatory. Now it has grown to a global community of more than 1,200 scientists from 55 countries seeking to, quote, understand the quantities, movement, forms, and origins of carbon in Earth, unquote. How much that is deserved to be celebrated today can be traced to Dimitri's brave and determined mother. Thank you.
How many of you had heard Tom Lehrer? Heard one? Only one? Only one in this whole room? Well, can you do it the way he did, the same way? To talk so incredibly fast? At any rate, I'm glad then that the other people haven't seen it at all. But that was pretty effective, I would think, to express about the natural world of elements. But I'll be glad to have any questions from somebody somewhere in this line up here. Does anyone want to sing a little like? Well, here's one. I guess I have to pass this. Good.
Thank you for your lecture, for your video lecture.
Yes.
Okay. Many of people here, I think, want to know what you have done in this world, so you were awarded by Nobel Prize.
Oh, okay. Yes. I can tell you something like this. Ordinarily, we do chemistry in the old days as great mobs of molecules interacting with each other, and you may get, say, molecule A react with molecule B, make a molecule C, but whoops, before you can do other things, C may A with B or B, C, on and on. You can't tell what are the really definite elementary reactions that way. As a undergraduate, I had a professor who stressed that fact, that you had to try to track out all these different steps for elementary reactions. Something I learned in a physics course, but it was a remark by a professor. It was just 2 minutes or so that made me realize that something called molecular beams could do this. What you do is you get a box like this, pump down to vacuum, not terribly vac, but pretty good vacuum, and then you squirt in little beams, we call them, of molecules that come from little nozzles, and have slits to hold them. So you have a stream there. If the molecules were, you could imagine, our size, then the molecules traveling in the beam is pretty far apart, like 20 meters between us and such beams. So a lot of senior professors, when we tried to do this, to cross one of those very thin beams by crossed with another one, say beam A, beam B. The ones that collide, you only get one chance to collide once, and then it flies to your detector. The detector is the most important thing, of course, because you can see very low yield, right, for ordinary kind of thing. The first experiments we did, one beam was this long, another beam was about this long, and then the flight to the detector was about that far. And if you could collect the products from the reaction, it would take you a month to get one monolayer of molecules. So a lot of senior professors thought it was a lunatic kind of thing to do. But you know what? There was a detector. The detector is the same thing as in this couplet. A filament of tungsten will take an electron away from potassium hydride, if that's the product, with 100% efficiency. And it does not detect anything of the, say, oil molecules from our pumps that aren't good enough. They don't react to the tungsten. It only reacts with alkali species.
So what would the
So-
elements in your beams?
Beg your pardon,
The
ma'am?
elements in your beams.
The reactants were a tungsten atom beam and a methyl iodide beam colliding, and the product produced potassium iodide plus methyl. We only needed to detect one of the products if you can tell what the other one was, the methyl in that case. Years later, we were able to do it much better. We were able to detect molecules, not necessarily halogens or anything, that would allow us to detect molecules in a cubic centimeter. You just, if it's so weak, we can still detect. I could tell you how we got to that, but what we started 60 years ago, answering your question using the tungsten thing, allowed us to do it. And it's really startled people. And over a span of about 8 or 9 years, we had an instrument that could detect all kinds of molecules with very special ways to do it. We combined a lot of things that physicists had been doing for our molecular beam detector system. That's maybe more than you wanted to know about that, but
Beams
that's
have,
the essence of it.
beams have spread around the world in laboratory.
Oh, my wife points out that I should say these beams like this are spread all around the world now. When we called the first beam beyond all this, we called it Hope, and now there are about 100 or maybe 150 laboratories use that kind of beam all over the whole world. So another question?
Thank you very much for the lecture. It was very informative. Yet, I would like to ask you about the World Scientist Warning to Humanity, which you signed with fellow Nobel Prize winners, and it has been signed more than 30 years ago. And I would like to ask you, has anything changed? What can we do to improve the situation, and what is the main problem identified in that document, like from your point of view? I'm talking about like the world scientist warning to humanity that you signed with fellow Nobel Prize winners. 30 years, around 30 years ago, which identified the main problems that humanity should address.
Well, we aren't able with a molecular beam to deal with problems of those kinds. We of course, deal with molecules and chemistry and all, but those things do contribute to learn a lot about chemistry, even that kind of chemistry that deals with what goes on in our own bodies. So more and more you gain information of that kind. So that's the best I can say about the sort of thing connected to what started with the tungsten and platinum posted way back 60 years ago. Well, after a while, you can get something that's very different and much better than you ever imagined what you have. I think another.
Hello, Professor. Thank you very much. I will ask you some questions personally. I know that Nobel Prize is like the higher prize for all the scholars, all the scientists. So I want to ask you, how do you feel after the Nobel Prize winner? I mean, do you feel any different from your life before Nobel Prize and after Nobel Prize? Will they influence your scientific research? How do you influence your family, and how do you influence yourself?
Yes, well, people often ask you that if you get a Nobel Prize, but I had always been talking with my students when it comes to things about prizes and so forth, that really the prizes should go to the molecules or ideas, but instead, since they can't do that, they give it to people who represent it. And of course, there are many, many very fine scientists don't get a Nobel Prize, which was very, very good, but that's the very nature of things. Actually, now there's so many very big prizes. One, for example, it's a breakthrough that's $3 million, whereas the Nobel Prize is only 1 million and usually divided between 2 or 3, so on. So the main thing is to just realize that whatever you do, it doesn't really matter in the end. It's what matters for the whole society. And some people will happen to get this, someone else. But when you do happen to get such an award, then it's up to you to try to represent the whole kind of scientific behavior. And I think most times that's what happens, that the people at Nobel try to do things right and help other people and all the rest, and make lots of other nominations and other things, many other prizes and so on.
But the Nobel Prize is why you were invited here.
Well, yes, Jane points out that it's the reason that I'm here talking to you, because otherwise there'd be some other Nobel Prize. That's all right, great.
Good afternoon. Thank you for your lecture. Now I have a question. What do you think? How do you think? Which parts of chemical technology are popular and actual nowadays?
Okay, did I quite? My ear is not as good as it should be.
Which parts of chemical technology are popular and actual nowadays?
What kind of chemical technologies are popular nowadays and most popular?
What
Kind of chemical technologies?
I think he was saying something like it would be the most popular molecule or reaction that people like to do nowadays. Is that what he had in
what sort
mind?
of projects?
What sort of technologies?
What sort of technology is most popular today? There's a whole variety.
Well, yeah, he was asking whether there are chemical technology that is much very popular these days. Nano, I was just about to say, nano is very much that way. We have a colleague at Harvard, for instance, who has done incredible things with nano molecules and wiring and all. They can wire your brain, with nano wires of all kinds. So, there's a lot of work now, at least in Harvard, all about people's brains. Chemists working directly in the brains. That's one thing.
How about drug delivery systems like Bob Lander and Maria in Spain?
Yes. At Passion for Knowledge, where we had this week before, there was a woman who made a very interesting description of a way of bringing in material that can attack the cancer in bones. Actually, you can travel a molecule that doesn't do anything until it finds in the bone the thing that it wants to get rid of. That's really wonderful, wonderful. So it's clearly a very valuable way to get a drug for fixing up your brain, your bones, lots of other things. So what's so marvelous about science is that there's so many things waiting here. You don't know what's going to happen, but you keep working on them, and little by little, someone finds this, and someone else something else, and you put something else there, and well, marvelous things appear. Here's another.
First of all, I would like to thank you for the lecture just given. Very interesting, very informative, just la around. But at the same time, I'd like to ask you a question. The scientist. You're a scientist, I'm not a scientist. I'd like to ask you, the scientist. So, why did you become a scientist? And the second question is, why can't anyone become a scientist? I mean, are people born scientists, or can anyone become one? There's enough dedication and doing that.
Yeah, why did you become a scientist?
The question was more like, why did I become a scientist? Well, I was turned 11 years old, and at my grandmother's house, they had a National Geographic article, and it had Heavens Are Above, and it had beautiful maps with the constellations of the stars. And I felt immediately interested with that. And so I started reading books and so on about planets and all the rest. And it just made me terribly excited. I got a little tree in the backyard I used to climb up to look at the stars, and I would prick a little pencil prick points for the constellations but I just hold on the side and just click quickly to get the pattern, so I didn't want to make my eyes not operating properly. And so I did that, and it got me more interested, very interested in science. I always have thought that when you are a young person, the joy of discovering things in nature, plants, animals, stars, all these things, realize, gee, I'm some kind of creature, all this nature everywhere. And if you realize, well, I'd like to learn a little bit more about and so on. So at the school I went, grammar school, was a class of only 11 kids a class. They graduated with 11 kids. And then at high school, one level was about 100. And so, and I wound up going to university, Stanford, and I was recruited to be a football player, and that involved collisions with people, and so that may have had something to do why I got interested in colliding molecules a few years later and so on. But I just kept realizing how many wonderful things you can learn. And back in my time, undergraduate chemists weren't required to do anything to get calculus to use for thermodynamics and so on. But I soon discovered that it was so much more interested to follow mathematics too. For example, probability theory. When the summer after my sophomore year, I was invited by my colleague, my mentor, to work in his lab, and he heard the graduate students all talking about something called quantum mechanics, and it involves probability theory and all that. And so I immediately signed up for that, and the teacher was George Polya, a Hungarian, wonderful teacher and also fine mathematician. And I was just enhanced by that fellow. And I just do the general principle that if there's a Hungarian course, take it. And so I actually wound up eventually. There were more Hungarians at Stanford. That I actually wound up taking 5 math courses along with 5 other courses, because mathematics is it's like music. It's easier and easier and so on. It's wonderful. So I couldn't have, so that made a big impact. I could use that a great deal in later life, because I wound up, when I went to be a graduate student in chemistry and physics, I had done so much mathematics that I didn't have to do those courses anymore. I knew them all. That was a big help. Anyway, I'm talking out too much for your question. I'm afraid I had another question. I think the young woman here.
Thank you for your lecture. It was very interesting, and my question is very specific. Do you have any favorite elements?
Yes. You want to guess which one? Do you want to guess the one I guess?
Is it active? Because my favorite is cesium, because it's the most active and it's stable.
Yeah.
It's francium.
That's very good. But hydrogen atom is my favorite. It happens to be the most prominent one in the whole cosmos. About 92% is hydrogen. So helium is next, 6%, and all the other things are less than that. pointing out.
There's a question.
Yeah, I see it. 1, 2 here. Well, I think someone wants it over here. If you get to pass it over to her. Yeah.
Thank you for your wonderful lecture. Can you tell me how much you worked the efforts you make to get the Nobel Prize? Because I think in the future to become a scientist like you.
Well, I made no idea, any question about the new Nobel Prize. I didn't expect it.
Do what you love to do.
I had, sorry?
Do what you love to do.
Yes. I mean, it was so exciting with the things I learned in mathematics and admiring a lot work of lots and lots of other scientists in the various fields and all. So I wasn't thinking about the Nobel Prize at all. Actually, it was a fun way. The phone rang. I was actually getting ready to go to class, and the secretary called and asked a reporter who wants to speak to you, and he called on the phone and said something about the Nobel Prize, and I had in previous years had a call like that by somebody to say, call Dudley, he'll tell you this about some laureate that Roald Hoffman said that 5 years before. Anyway, so the upshot was that I asked the guy, well, who got the Nobel Prize? Oh, I did. A big surprise. And of course, I asked and learned that John Polanyi and Yuan Li shared it, which was even better than the Nobel Prize as far as I was concerned, because I admired those people so much. There are other people in the field who certainly are deserving as well, but you don't get more than 3 by the Nobel Prize thing. So I called a couple of those people and talked about it and so on, but they weren't too happy. Can't help it.
Yeah.
So
just do what you love.
Yeah.
Don't expect the prize.
Yeah. What matters is if you're in love with what you have the chance to do, and work with people who are like that too, and not concerned about prizes, but learning things and seeing things in a new way. That's the precious thing. I think she's waiting for another question. Thank you.
Professor, thank you so much. It was a real pleasure to hear you here. And my question is about difference in epochs. Like Mendeleev time was very special for science. It was a time of blooming of scientific societies, conferences. He was friends with many great people of that epoch. And it was a kind of free time for science, when classical science was forming. Great human environment of that epoch, I think, was very, needs to be considered in his achievements.
Yeah.
And now, on the other hand, we sometimes find ourselves in a situation when we have to produce something for industry, when modern scientists already ordered to produce something for research, yes, to fulfill the needs of industry. It is a system working is not so free situation and not so free fashion. Do you think that for fundamental science it may be kind of a problem? What do you think of that?
Okay, sorry, I may need a little help to...
I think she's saying that scientists now are required to produce results for industry,
Ah.
but there's not a big
Yes.
free. But in academic science, you follow your questions and your own ideas.
Yeah. If I wasn't able to hear too well, but you were concerned about having to do things for industry, actually get something done that they want done, that kind of thing. But of course, that's the important thing about the academic research, that it's, you don't necessarily have to achieve doing a particular thing. You can discover it in academic lab. Yeah.
I'm ready to tell you that the question is about a situation when academic research is ordered from industry, when not not the scientists is somebody who decides what to research, but when industry orders him to a group of scientists to research something for industry.
Yeah.
Is that because the funding comes from industry?
Yeah.
So that's different. If funding comes from industry, they want a particular experiment.
Yes. So the funding comes from industry or whatever because they hope that you do a certain thing. But it seems to me, let's make an argument. We'll tell them that if you look at chemistry and so on historically and all the rest, you realize that an awful lot of things are found in academic work that turns out to have a big impact for industry.
That's curiosity-based research.
Yes, the curiosity-driven thing that you can do in academic work.
Yeah.
So if the industrial people will realize, they would say they should give a certain amount of money where you can do whatever you want with it, and then you do as much as they would like you to. Here's another thing about tungsten, for example. A fellow named Irving Langmuir was hired by GE Electric years ago, around the turn of the century. There was this concern to get out light bulbs to light the cities. And the bulbs, many of them were trying with tungsten, but the tungsten actually would just vaporize away on the tube inside, and the filaments burn away rather quickly. It looked like it was hopeless to getting that kind of lighting of the cities. But this young guy realized that what they had this bulb, they pulped out the bulbs, will be stopped. If you put in argon or nitrogen, they will stop the tungsten from vaporizing. And it was able to make thinner filaments than before. And after a while, they had much better light. That made billions of dollars from GE, from this guy, this one guy. And then they let him do anything he wanted, anything he wanted to do. So that would be nice to do, but he did a lot with other things. Well, are there some more questions?
Good afternoon. So I'd like you to ask a kind of personal question. So what kind of advice would you personally give to young people who want to become scientists?
personal advice to young people who want to become scientists?
Yeah. Well, the question I think was what you want to do to become a scientist.
What's your advice?
Beg pardon? Yeah.
What's your advice to a young person who wants to become a scientist?
That's right. Yeah. The question is, if you want to become a scientist, you want to be patient. You want to be patient, studying things that you feel are interest aspects, the kinds of science that appeals to you. But you have to be patient, because if you keep working with it, you may find something else. Because if you read and study and so on and see other things, you may well recognize something that and nobody else has spelled it out. And you recognize that, oh, I'd like to try this, and so on. So it's good if you can do it with an experiment or a mathematical experiment. I mean, nowadays, with equipment you can find, you can do amazing things. So that's one aspect. But finding mentors and as teachers or other students, if you interact with them a lot with it, that helps you a great deal to decide what kind of thing you want to do. Because it's kind of like this. It's a little like to be a musician. To become a good musician, I don't mean I ever turning up the knob, just someone plays and says something good. You have to practice and all that, you learn. But in chemistry, when you're working on it, or science, you may get most of the notes wrong, and no big problem. But if you get a boat right, then apply. So you see, that's a pretty remarkable aspect. Another way of looking at it is some idea that you have or whatever is kind of like an enzyme molecule. An enzyme molecule, you have lots of enzymes in your cells, but usually only one or two enzymes of that particular molecule in your cell. And that molecule has to wander around, bumpity, till it finds the molecule that the enzyme is catalyzing for. Enzyme is a catalytic protein molecule. And so if it finds the thing that will catalyze, you can produce something more than, say, 10 million product out of that molecule. But you have to be patient again. The enzyme has to bounce. Oops, I found. So it's something like that when you're doing science. You know, that's just part of it. So I don't know what this fellow is doing. That looks rather dangerous.
This fellow.
Ah, yes.
Well, thank you for your lecture. So it was very interesting. Also, thank you for your honor given to Mendeleev. I have a question, probably personal too, and something you probably have answered already. But my question is which things were of a great help to you to reach your great results in science? And what are those essentials without which your breakthrough maybe reached much harder? Like I emphasize probably the question answered before, that is great. What are the most essentials, the most essential things which help you to reach your great results in science?
Yeah.
Personal things.
Well, it had an awful lot to do with my mentors and the students, postdocs, and undergraduates and so on, working with me, because we all worked together. And that was a wonderful part of it to begin with. I'm not quite sure that I picked up your question.
Maybe you have a great atmosphere in family which helped you.
Oh, he's asked whether people in your family that helped you, but you should say you're the first person in your family.
Well, yeah, sorry. I was the first of 6 kids. We never had met anyone who graduated from college at all. So I was the first one to go to college. I mentioned that already. I'd been at various small schools that I'd gone to. Now, Georgine also came from a family where none of the people knew well. So she went to university and went on to get a PhD, and I did too. And one of my brothers, he also went off and got a PhD, and his children got 3 PhDs. Our daughters got PhDs. So, and the we have 5 grandkids, and looks like likely some are going to be PhDs and so on. So we started totally. It was like the National Geographic thing, getting excited about the stars. So just take a fling, do what you can with it. So I think there's another. Yeah.
If I may, one more question. Mendeleev has had a funny hobby. He was really fond of making leather suitcases. It was his hobby. Do you have some kind of funny hobby?
Mendeleev had a hobby of making suitcases.
Suitcases?
Suitcases.
And what
Yes,
is your hobby? What is your hobby?
What was your hobby?
Oh.
Your hobby was playing football.
Well, that was one. I did a lot. My hobby was I did a lot of camping with Boy Scouts, and did lots of sports. I was a football player, American football, and I loved to catch the ball and so on. And actually, when I was getting invitations to colleges, some of them came I hadn't applied to at all, but I was a good football player. They invited me to come. But it turned out that my high school was very, very good on grades and so forth. And so I got an academic scholarship. Academic, right. I had been at first given an athletic scholarship, but it turned out that they gave me a larger scholarship than the athletic one. To be a scholar. So I didn't have to continue with football, although I loved doing it, but it takes much too much time on varsity football and these top teams like Stanford. When Stanford had a pretty good football team, But when they arranged to have Harvard play Stanford, Harvard lost by 44-0. I think our high school could have beaten Harvard, but at any rate.
You should also say you came from a poor family.
Oh, well, yes.
And university was very expensive.
Yeah, right. My parents couldn't support any of the students, any of their kids to go to schools. I was able to help them.
Yeah,
I really was.
It's expensive in the U.S.
Yes, of course, it's now vastly more expensive now than it used to be. On the other hand, there's still lots of scholarships that are offered to good students who work hard and all. So, you know. Okay. All right. Well, thank you.
Question is about what do you think about connection between philosophy, history, and chemistry and science? I mean, when I was in China, I met some professor who told me that if you want to study science very well, you have to understand philosophy, history very well, so that you can just understand modern science well. And I didn't quite get it, so I was thinking, what do you think about the connection between philosophy and science? And do you personally really like science? Do you personally really like philosophy, or do you know many about history?
Yeah, the question is whether philosophy is very important.
It's like quite different opposite field. Yeah. It's totally different, but I really want to know.
You need to study philosophy and history in order to understand.
Because I was once told by a professor who is also very good professor in China, and he told me that if you really want to understand science very deeply, you have to study philosophy. And most of the very good scientists, they know philosophy very well.
Yeah.
So I actually didn't quite get it. And actually now, my last favorite course is like chemistry, history, and I really don't like it.
Yeah.
Okay. So
Well, yeah, let's see. There's some very nice papers you'll study by scientists that are all about philosophy, how important philosophy is. So, you know.
The question is you need to understand philosophy to do chemistry.
But the question is, do you have to do chemistry unless, if you don't do philosophy? Well, I'm not so sure that's true. There are people who don't really do it that way, but other people do. Have written, real philosophy people really count. Matters is important for them if they do that. But I'm not sure that to have to be a philosopher. It'd be more or less, if you can sing, that may help you with science. But if you don't sing, that may not matter either. So really, I think I like philosophy myself. Yeah, history a lot. Right. I fell in love with history.
You don't think studying chemistry, history is really good for studying science?
You don't have to have history to study science.
You have to discover yourself, right? It's a philosophical thing, if you want to call it that. You have to discover who you are. And so it's good for you to read philosophy, history, all kinds of things, as well as science and math. That's what's going to happen if your body and brain and all react to it. So I think basically that's what happened, really, when you discover things. Yeah.
We thank you for your We thank you for your great contribution to the scientific world and your visit to the chemical department. Давайте поаплодируем.